This short tutorial is going to try to explain how marginal utility and marginal rate of substitution are related, and we're going to use a concept from mathematics called the total differential. Okay? So I want you to imagine that you're looking at an indifference curve. So this is just a regular indifference curve where we have two goods, x and y, and these two goods are depicted in this particular utility function right here. Note that the picture is not drawn exactly to scale. It would be a much more sort of symmetrical picture for this utility function, but you get the idea, I think. We know that our typical approach to drawing an indifference curve, once we're given this utility function, is to set the utility level equal to a fixed number, and then to solve for y. So here is y equals 10 divided by x, and that is the equation for our indifference curve, right? Next, if we want to know the slope or the marginal rate of substitution, we would take the derivative of y with respect to x, which we call dy dx in our notation right here. And if you get comfortable with negative exponents, that's the easiest way to do this. So we can rewrite this as y equals 10x to the minus 1 power. And we would write it that way because then we can use the power rule to compute dy dx. It would simply be minus 1 times 10 x to the minus 1, or minus 2. So here or here are equivalent expressions of dy dx, and that's just the marginal rate of substitution, which we also know to be the slope of the indifference curve. So have that in the background as we move on to the next step here. Next, what we're going to do is we're going to try to relate that idea of the marginal rate of substitution to the marginal utilities. All right, so we're going to develop this problem a little bit differently than we have so far. Right, so what we're going to do is we're going to start with our definition of the utility function, which we saw earlier up here. That's this thing, right? And we're going to, in general, create an expression for what we call the total differential. Now I want to distinguish the total differential from a partial derivative. A total differential is trying to take that utility function u of xy and imagine what the total change in u would be if we allowed for small changes in both x and y simultaneously. And we'll contrast that with what we know to be a partial derivative, which is the change in utility when we let x change by a little bit, holding constant the other variables, in this case just y. So in this case, change in u when x goes up by a little, holding y constant. When we look at the left-hand side, we're thinking about a change in u when we allow both x and y to change simultaneously. So the total differential is an expression that shows how u will change if x and y are allowed to change at the same time. And this particular expression here, okay, let me clear this up for you a little bit. This particular expression is going to have two distinct components, and within each of those there will be two distinct components. So first we're going to examine the change in u due to a change in x, okay? And I want you to think about this dx as a small change in x, okay? It's actually a physical small change in x. This we know to be the partial derivative, which is a rate of change. So this tells us how does u change when x grows by an infinitesimal amount. So when we multiply the rate of change of u with respect to x times some actual change in x, that's the way I want you to think about it, what we end up with is the total change in utility. That's what that whole product is. The total change in utility resulting from specifically a change in x. Okay? Now we do the same thing for y. We have the rate of change of u when y goes up by a little bit, and when we multiply that times an actual change in y, we get the total change in u due to a change in y. So the whole thing is the change in utility from a change in y. When we add those two things together, we get the total change in u. Okay, so this is just a way of expressing the change in utility when x and y are both simultaneously allowed to change. Okay. Now, what we're going to do is apply that to a single indifference curve. Except I can't. There we go. We're going to try to apply that to a single indifference curve. But before we do that, let's try to relate this back to marginal utilities if we can. Okay. So first of all, the partial derivative of u with respect to x is in fact the marginal utility associated with x, and this is the marginal utility associated with y. So we can rewrite that total differential in terms of not partial derivatives but marginal utilities, because by definition marginal utility of x is the partial derivative of u with respect to x, and same for y. Okay. Next step is to look at this. So I've gone from du, what is my change in utility, to 0. Now why did I do that? Well, here's where we're going to try to take this expression for a total differential and relate it to a single indifference curve. And when we look at an indifference curve, what do we know about the utility at all of these different points along that indifference curve? What do we know about those? Well, we know that utility is not changing. In other words, the change in utility for a given indifference curve is 0, which justifies our setting this expression equal to 0 right here. Once we do that, we can do a little bit of algebra by taking the dy expression and leaving it on the right-hand side, moving this over here and putting a minus sign in front of it, subtracting it from either side, for example. And when we rearrange it further, I'll let you do that on your own, you end up with this particular expression. Well, dy dx, if we're holding utility constant, is just the slope of the indifference curve. It's just the marginal rate of substitution. And we have now shown that that marginal rate of substitution must be equal to mux over muy. Okay? So this particular way of thinking about marginal rate of substitution relates it to the ratio of marginal utilities. And I want you to think about what that implies regarding diminishing marginal utility and diminishing marginal rate of substitution. In other words, if x and y are both characterized by diminishing marginal utility, how will that imply that the marginal rate of substitution changes as we add x and remove y from a bundle?